Hello friends, I am Professor Rajendra Koranne from my YouTube channel Teach Easy. In the previous video we saw the step-by-step procedure of design of one-way simply supported slab. In this video we will see step-by-step procedure of design of two-way simply supported slab. Let us take an example. Design a reinforced concrete slab panel for 6.3 meter by 4.5 meter, simply supported on all four sides. It has to carry a live load of 4 kN per meter square in addition to its dead load. Use M25 concrete and Fe415 steel. Take alpha x is equal to 0.099 and alpha y is equal to 0.051. This problem is asked in MSBT exam for 6 marks. Now this is the problem on two-way slab. A two-way slab is one which is supported on all four sides, and therefore the load on the slab is transferred in two perpendicular directions, along shorter side and along longer side. Therefore, it is known as a two-way slab. Okay? So, let us start how to solve this particular problem. Now, as usual, let us list out the given data. Now, what are the things given? Let us see. Now, here slab panel is given, means the effective dimensions of that particular room are given. Now, the smaller dimension is taken as Lx. Whenever we are designing the two-way slab, the span for two-way slab is taken as the shorter span according to IS 456-2000. Lx is given as 4.5 meter. Ly is given as 6.3 meter. Intensity of live load is given 4 kN per meter square. In addition to dead load as it is given in the problem. The weight of floor finish is not given in this case. The grade of concrete is M25, therefore FCK is equal to 25 Newton per mm square as usual. Fy is also given. Grade of steel is Fe415, therefore Fy is equal to 415 Newton per mm square. Okay. Similarly, bending moment coefficient alpha x and alpha y are also given. Now, this is a problem of 6 marks, no checks are required. Okay. So, what is the required thing to design the slab? Means we have to find out overall depth of the slab and reinforcement. So, this is the problem. So, let us start solving this particular problem. So here these effective dimensions are given, so let us find out Ly upon Lx, that is 6.3 divided by 4.5, which comes out to be 1.4, which is less than 2. Therefore, design the slab as a two-way slab. Okay? Now, let us start with our steps. Step number 1, trial depth. Now in one-way slab, I have already shown you the page in IS where it is given that the basic L by D ratio for simply supported slab is 20. Okay? Now, what is trial depth D? Trial depth D is equal to, span should be taken as shorter span Lx upon basic L by D ratio, B for a basic, into modification factor. Okay? Now we know that here in this case L by D basic, as it is simply supported, is 20. Okay? Now you have to please see one thing. If MF is not given, it is to be assumed as follows. Now, how this is assumed? This is assumed as per page number 38 and figure number 4. See, look here, you can very easily see that this is page number 38 of IS 456. This is figure number 4. Here different curves are given, modification factor, percentage tension reinforcement. So you have to assume that percentage reinforcement and accordingly you have to assume that modification factor. Okay? So let us see what is that modification factor, how it is assumed. So this is what is given as per IS. So it is to be assumed as follows. Now what is as follows? Look here now. Okay? So for different grades of steel, that is Fy, and for different percentage of tension reinforcement, I have just shown you the curves on page number 38 of IS, and this is modification factor. Now how it is to be assumed? Look here now. So for 250, Fe 250, that is mild steel, percentage PT is to be assumed around 0.9, and for that purpose modification factor is of 1.5. If it is Fe415, percentage PT is to be assumed as 0.35 and AMF is to be assumed as 1.4. And if it is Fe500, percentage PT is to be assumed as 0.28 to 0.3 and modification factor is 1.25. So this is a very important thing in which we are given I have given you what should be the value of modification factor to be assumed when it is not given. Please see carefully. For all the three grades, I have told you, if it is not given in the exam, you can assume percentage PT for the given grade of steel, and accordingly you can assume the modification factor. Okay? So, now here we are using Fe415. So, what I will do? Assume percentage PT is equal to 0.35. Therefore, what should be the value of modification factor? It is to be taken as 1.4. Okay? So this we have assumed. Whatever things are assumed, you have to check it whether it is correct or not. Okay? Therefore, now we will calculate the value of D. D is equal to Lx is 4500 divided by basic L by D ratio is 20 and modification factor is 1.4. If you calculate this value, it comes out to be 160.71 mm. Say 160 mm. Okay? So this is the value of small d. In one-way slab, I have shown you what should be the effective cover. So I will say that assuming effective cover of 20 mm, okay, assuming effective cover of 20 mm, overall depth capital D is equal to effective depth 160 plus effective cover 20. Therefore, overall depth is 180 mm. So, this is the first step. Okay. Now, let us go for the second step. Now, what is the second step? Load calculations. Now, as usual, consider (1 meter) wide strip design load. Now, I will directly write the formula which I have already explained you in one-way slab. Design load WD is equal to 1.5. This is for making ultimate into bracket 25D. This is self weight of the slab plus live load plus floor finish. This will be the load in kilo Newton per meter. Let us continue this second step. Therefore, design load WD is equal to 1.5 into bracket 25 into D. D is overall depth in meter. Here D is 180 mm. Okay. What is D here? D is 180 mm. So 25 into 0.18 plus live load. Live load is 4 into 1. No floor finish is given. So let us calculate this. This is equal to 12.75 kilonewton meter. So this is the design load. Now let us go for the next step, step number 3. That is design moments. Now this is a two-way slab. Load is transferred in two perpendicular directions. Hence we will have to calculate two different bending moments along shorter span, along longer span. Okay. Now how to calculate bending moment? For that purpose, again I will show you. This is annexure D of IS 456-2000, slab spanning in two direction, that is two-way slabs. Okay. When the corners of the slab are prevented from lifting, the slab may be designed as specified in D.1 to D.11. Okay. Now actually here we are not preventing the corners. Two-way slab, corners are free to lift, they are not held down. Due to partial fixity at the corners, the slab may get twisted like this. Okay. And to resist such type of torsion, special reinforcement is to be provided at corner. That is not in your curriculum. Hence we are designing a two-way slabs which are not prevented from lifting, that is they are free to lift, not held down. For holding them down, special reinforcements are required. Now you can see this, mx is equal to alpha x into w into lx square, and my is equal to alpha y into w into lx square, where alpha x and alpha y are coefficients given in table 26. W is total design load per unit area, and mx and my are moments on the strips of unit width spanning Lx and Ly. Okay. So this is given on page number 90 of IS 456-2000, and it is given in annexure D. Okay. So according to annexure D, we will calculate first BM along shorter span. BM along shorter span. That is along Lx, which is known as mx or mdx, d for design moment. So mdx is equal to, as shown on page number 90, it is alpha x multiplied by w, that is wd in our case, into lx square. Okay. We are given the values of alpha x. Alpha x is given as 0.099 into WD. WD is 12.75 into Lx square, that is 4.5 square, which comes out to be 25.56 kilonewton meter. This is the design moment along shorter span. Okay. Now let us calculate the design bending moment or bending moment along the longer span, that is MDY. BM along a longer span, or design moment MD BM along longer span. Which is denoted by My or Mdy. D for design, Mdy is equal to, mind well, only alpha x will change to alpha y. Wd will be as it is, and Lx square will also be as it is. Please mind carefully that in case of Mdx it is Lx square, therefore in case of Mdy it is not Ly square, it is Lx square only, because we are designing the two-way slab for the span Lx. Okay, so let us write the values. Value of alpha y is given as 0.051 into Wd is 12.75 and Lx square means 4.5 square, which comes out to be 13.17 kilonewton meter. Okay, so this is the bending moment along longer span. Now, as far as the examination is concerned, either the values of alpha x and alpha y are directly known, or you are given the table in the examination in question paper, which is as per page number 91 of IS 456, table 27, bending moment coefficients for slab spanning in two direction at right angles, simply supported on four sides. Clause number D21. So here you will see Ly by Lx are given, alpha x, alpha y, and for Ly by Lx values 1, 1.1, different values of alpha x and alpha y are given. If you carefully observe this table, you will find that as Ly by Lx goes on increasing, alpha x goes on increasing, but alpha y goes on decreasing. So very clear that for Ly by Lx is equal to 1, both the spans will be same. So alpha x and alpha y are equal. Okay. So this is as per page number 91 of IS 456, that is from BM coefficient from table number 27. Okay. So you are given the table and you have to calculate alpha x, alpha y, and then by interpolation you will calculate it if the value is intermediate. Or you can also calculate alpha x and alpha y by the formulae. Okay. So this I will give you. Alpha x and alpha y can also be calculated. If they are given, it's okay. Also be calculated as follows. Okay. So what is the formula for alpha x? Okay. So if I say if Ly upon Lx is equal to R, then alpha x is equal to R raised to 4 upon 8 into bracket 1 plus r raised to 4. So I have just told you that as Ly by Lx, that is r, goes on increasing, alpha x goes on increasing, and alpha y decreases because it is calculated as alpha y is equal to, instead of r raised to 4 in numerator, it is r square, and denominator remains same, that is 8 into bracket 1 plus r raised to 4. Now this is not applicable here because it is given in this problem what is the value of alpha x and alpha y. Okay. So in this manner we have calculated the bending moments. Okay. Now let us go for the next step, that is reinforcement. I have already told you that we are designing a slab whose corners are free to lift, they are not held down. So we will not be providing any special torsional reinforcement at corner, okay, because the slab is free to lift. Okay. So first one, reinforcement along first short span. Okay. So I will write that cinemascopic formula. ASTX, because along short span, is equal to, what is the formula? 0.5 FCK upon Fy into bracket, come on, 1 minus under root of 1 minus 4.6 mdx upon FCK BD square, bracket complete, multiplied by B into D. We will put all the values, is equal to 0.5, FCK is 25 divided by Fy is 415 into bracket 1 minus under root of 1 minus 4.6. What is MDX? 25.56. Mind well, it is in kilonewton meter, so it must be converted into Newton mm, that is multiplied by 10 raised to 6 divided by, again, FCK means 25, B means 1000, and D square means 160 square, bracket complete, into B into D, that is 1000 into 160. So with the help of scientific calculator, you will get ASTX equals to 465.13 mm square. Now again, let us check it for minimum area of steel, AST minimum is equal to 0.12% of BD because we have used HYSD bars. So if you put the values, 0.12, B is 1000, D is 180, divided by 100 for percentage, which comes out to be 216 mm square. Now you can very easily see that we have checked the value of AST for minimum value of AST, and we found that the calculated value of AST is greater than AST minimum, hence it is okay. Do you follow this? We will calculate the spacing, okay, that is spacing of short span steel. For that purpose, let us say that use 8 tar bars having, what is area of 8 tar bar? Area of 1 8 tar bar, small AST, is equal to area of 8 mm bar, pi d square by 4, you can do it as 50.27 mm square. Therefore, spacing how do we calculate the spacing? Spacing is equal to 1000 into small AST, that is 50.27, upon capital AST, which we have calculated as 465.13. If you do it on scientific calculator, you will get this value as 108.08. Say you will have to round it down, 105 mm. So this is the spacing of 8 tar bars, okay. So this spacing you will have to check for maximum one, okay. So again, spacing is equal to 105 mm. Now what is the maximum spacing? First one is 3D, which comes out to be 3 into 160, that is 480 mm. And second is 300 mm. Whichever is less. So out of these two, this is less and this is not greater than 300. So this is okay. This is check for maximum spacing. It is same as we have done for main steel in one way. Okay, so this is okay. So spacing is also checked. Okay, so you can very easily see that. Use 8 Tor bars at 105 mm center to center along short span with alternate bars bent up. Okay. Now part B of reinforcement, that is reinforcement along longer span. Now, as this is a two-way slab, load will be transferred in two perpendicular directions. Hence, in both the direction, main steel is provided. Okay. First one, along shorter span steel is laid, and over that the steel along longer span is laid, but both are main steels. Now, one important thing you have to do as far as reinforcement along longer span is concerned is, for longer span you will have to find out the effective depth once again. See, look here. This is the slab. Okay. Now you have taken this cross section along longer span. So you will find that these are the main bars along longer span, and these are the main bars along shorter span. Okay. Now here you can see that this up to the center, this D is 160, but as far as the longer span is concerned, this will be dy, that is effective depth. Now you can see here half the diameter of this short span steel and half the diameter of long span steel. Okay. So effective depth As it is along longer span, I will call it as dy is equal to the d which is taken along shorter span minus half the diameter of the bar along shorter span minus half the diameter of the bar along a longer span. Now along shorter span we have used 8 mm. Along longer span also we will use 8 mm. Okay. So using 8 Tor bars in both directions, okay. So what will be dy? Dy will be, what is d? 160 minus 8 by 2, that is half the bar diameter of the bar along short span and half the diameter of the bar along long span. So this will come to be 152 mm. So please keep in mind, if you forget this step in the exam, it doesn't make much more harm, only 1 or 2 marks will be cut. Okay, but actually I have shown you with the help of figure. So effective depth when you are considering longer span will be reduced. Okay, so again we will calculate ASTY by our cinemascopic formula. I will directly put the values now. 0.5 into FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 mdy. What is mdy? We have already calculated it. It is 13.17 kilonewton meter. So into 10 raised to 6. This is very important to convert it in Newton mm. Otherwise, your calculations will not be correct. Okay? Divided by FCK B d square. Multiplied by B, that is 1000, into dy, that is 152. Here also it will be 152 square. Please correct it. 152 square instead of 160, because we have calculated that. Okay. So if you calculate it, this comes out to be 246.75 mm square, which is definitely greater than AST minimum. We have calculated AST minimum already. Okay. Therefore, okay. Now, we will calculate the spacing of 8 Tor bars. We have already decided to use 8 Tor bars. Okay. Let's calculate the spacing. spacing is equal to 1000 into small AST, that is area of 1 bar, upon capital AST. We have decided to provide 8 torr bars. The area of one 8 torr bar is 50.27 and AST which we have calculated is 246.75. So if you calculate this, this comes out to be 203.75 mm. Say 200 mm. Now again you have to check this for maximum spacing. Okay. So maximum spacing is lesser of 1 3D, that is 3 into 152. Along long span effective depth is 152, which comes out to be 456 mm. And second, mind well, this is main steel, so second one is 300 mm. Lesser of the two is 300 mm. And the spacing which we have provided is not greater than the maximum spacing, therefore it is okay. Do you follow this? Step number 5. Check for D for BM. You can apply this step after calculation of bending moment also, doesn't matter. Okay. So for check for D for BM, now what type of steel we are using? Okay. So here how do we apply the check for D for BM? Equate MDX or MDY. Okay, whichever is more. Okay, you have to equate it with MU lim. for Fe415, MULM is equal to 0.138 FCK B D square is equal to, definitely whichever is more is MDX, hence MDX we know is, what is the value of MDX? MDX we have calculated, it is 25.56 kilonewton meter, 25.56 kilonewton meter. Okay, so we will have to convert it into Newton mm. Okay, therefore D square is equal to 25.56 into 10 raised to 6 divided by 0.138. FCK is 25. Into B, that is 1000. Therefore, D is equal to 86.07 mm. Definitely, this is the depth required to resist the bending moment, which is less than D provided. Therefore, it is okay. So, once you have checked it for greater value of bending moment, this will be satisfying for lesser value also. So, this is the check for D for BM. Hence, we also know that if you check it like this and if D provided is greater than D required for bending moment, definitely it will be an under reinforced section. Check for percentage PT. We have assumed percentage PT in the first step to calculate the value of modification factor. So, we will have to apply the check. Okay. So, for percentage PT, we will have to first calculate AST actually provided. AST provided is equal to, okay, this will be 1000 into ASTX, means area 1 bar provided along X, that is short span, divided by spacing which is calculated as 1000 into ASTX 8 mm bar 50.27, and what is the spacing along short span? It is 105. Spacing calculated was 108, but we have provided 105, so more steel is provided than that we have calculated by the formula, which comes out to be 478.76 mm square. This is actual AST provided. Therefore, percentage PT provided is equal to 100 into AST provided upon BD. So put all the values. So 100 into 478.76 upon B is 1000 and D is 180, which comes out to be 0.265. Now if you see carefully, this is less than percentage PT assumed. What we have assumed percentage PT? Percentage PT assumed was 0.35. Okay, this is less than this and therefore this is okay. Now all the steps are carried out. Now I have already explained you in case of one-way slab it is not necessary to check for shear for slab because slabs are safe in shear. So we have done it for sample purpose in one way. It is not necessary over here. So seventh one is summary. First, what is effective depth? Effective depth 160 mm. Overall depth 180 mm. Then reinforcement along shorter span. Short span reinforcement. Eight tor at 105 center to center with yes alternate bars. Bent up at 0.1 LX, that is 450 mm, from face of support. Okay, this is a short span steel. Now let us see what is a long span reinforcement. It is also 8 torr at 200 mm center to center with, yes, alternate bars. Bars bent up at 0.1 ly, that is 630 mm from the face of support. So this is the complete design, and the last step is to draw the sketch. Let us draw it. Figure which shows the cross section of two-way slab along the shorter span. See, this is the shorter span 4500. Now these violet color lines indicate the main bars along shorter span, that is main bars 8 torr at 105 center to center, and these red dots are the main bars along longer span, that is main bars 8 torr at 200 center to center. Now this 160 is the effective depth, 180 is overall depth. Okay. The figure shows the cross section of two-way slab along the longer span. This is the longer span 6300 mm. These violet are the main bars 8 torr 105 center to center along shorter span, and these red full lines are main bars 8 torr at 200 center to center longer span. Okay, so this is the cross section of two-way slab along the longer span.